So the next topic is hashing. Okay, so we are going to study hashing. So before hashing, just see if we are having an array of n elements. This array is having n elements which are 1, 2 up to so on up to n. Now in this array we are storing some data, maybe some numbers. For example, it is 1, 2, 3, 4, 5 up to n, and these numbers are sorted. That means we are having a sorted array. Okay, and in the sorted array, if you want to find some data, right? For example, if you want to find this data 5, right? So what is the best way to find that this array is containing the number 5? So what is the best way? So we can use the searching techniques, and the best searching technique for this is the binary search. So what is the binary search? We are going to see, we are going to take a middle point from this array, and then to that middle point we are going to see the data which we are searching is smaller than this middle point, or it is greater than the data which is present in the middle point. So if it is the data is smaller, then we are going to search in the smaller portion. And again here again we are going to perform the same operation, then again we are going to make it half, again we are going to make it half, up to so on until we reach the data item. Okay, now the time complexity of binary search is order of log n, right? So that is in the case of sorted arrays, right? What if you are having an unsorted array? That means there is an array where the data is not sorted, right? So in the case of unsorted arrays, so what is the time which is required to search some data or any data which is present into this array? Okay, the time which is required to search this data is order of n, because we have to do a sequential search. We have to search this data first, then we have to search this data first, then we have to search this data first, and so on. We have to do a sequential search in this array, right? But the question is, can you do something better than this? Can you reduce this time complexity? That is, can you make some kind of arrangement where the time complexity can be reduced from order of log n to something else? For example, you say order of 1, right? So to answer that question, there's a concept which came is hashing, right? In case of hashing, whenever you want to search any data, then it is going to take order of 1 time to search that particular data. Okay, now there are 4 key components in hashing. Number 1 component is the hash table. Number 2nd component is the hash function. Number 3rd component is collisions. And number 4th component is collision resolution techniques. Okay, now let us check all these things one by one. Now the first component is the hash table. So what is a hash table? You can say that hash table is a generalization of an array. Okay, within an array we can store the elements whose key comes to at some particular position. Okay, let me just not say anything like this. Let me just give you an example here. Okay, so assume that we are having this array. Okay, and this array is having some index locations, right? And these index locations are the index location 1, or say the index location 0, index location 2 up to the index location n-1. That means this array can store total n numbers, right? And this array is called as a hash table, right? So how this hash table is working is, so this hash table works with combination to a hash function, right? So what is a hash function? So assume that we are having some data which is 162, 196, 184, 93, 94, and assume that it is 695, make it this 97, and assume some other data. Okay, so we'll be using a hash function which is going to tell that which data must be placed at which location into this hash table. So what is a hash table? A hash table is an array which is going to have some index locations. Here in the case, the index locations are 0 to n, and we are going to have this data which we want to insert into this table, right? And this data is called as the key. So all this data is called as a key. So what is a hash function? Is if we apply this hash function on a particular key, then this hash function is going to give us a location, right? And on this location we are going to store this data, so that whenever next time if we want to search that a particular data is present in the hash table or not, we can just simply use this hash function to reach to that location, right? For example, here assume that we are having this number which is 162, okay, and let us assume that the size of the table is actually 100. That is, there are 100 index locations. That is, the index locations are 0 to 99, which is in total 100 index locations, right? So a simple hash function can look something like this. Simple hash function, you can say that it is key mod n, and this key mod n is going to return us some number, and that number will be the location where this data will be stored. Okay, for example, here we are having the key as 162. The value of n is 100, so we can say that 162 mod 100 is going to give us some number. So what is the number which it is going to give? The number is 62, right? So we are going to store this 162 number into the location which is 62. So let us assume this is the location 62, therefore we are going to store 162 here, okay? And the next number is 196. So what we are going to do is 196 mod 100. So when we did 196 mod 100, is going to give us the location 96. Therefore we are going to place this 96 number into a location which is the 96th location. The next key is 184. So this is 184 mod 100. That means it is going to give us 84. Therefore we are going to store this 184 at the location which is 84. Okay, so assume this is the location 84. So we are going to store 184 at that particular location. Okay. Now the next data is 93. So if we do 93 mod 100, then we are going to get the number as 93 only. Therefore we have to store this 93 number at some location whose address is 93, right? So assume that we are having a number which is 1000, and if you do 1000 mod 100, then we are going to get the number which is 0, because if you divide 1000 by 100, then you are going to get 0 only as a remainder. Okay. So in that case, we are going to store this 1000 at the index location 0. So in this case, you can see what is a hash function. So here the hash function is key mod 100. Okay, so this is a hash table and this is a hash function, right? So assume that we are having some keys like this. There are some keys which are 196, 182, 146, 147, 296, 31396, and assume let us these numbers are one more number is 1496. Okay, now this is our hash table, and this hash table is going to contain 10 index locations, right? So this is the index location 0, 1, 2, 3, 4, 5, 6, 7, 8, and there's one more index location which is the index location 9. Okay, now in this table the value of n is actually 10 only, because there are only 10 index locations. So if the first number is 196 mod 10 is going to give us the number which is 6, therefore this 196 will be stored at the index location 6. Okay, the next number is 182. So if we do 182 mod 10, then this is going to give us the number which is 2, therefore we are going to store 182 at the second index location. The next number is 146. So if we do 146 mod 10, then it is going to give us the number which is 6. But if you see, there is already some data which is present at the index location 6, and we want to insert the data 146, right? Now if we insert the data 146 into this 6th location, then this original value which is already stored into the 6th location, it will be overwritten and we are going to lose that value. Okay, so the problem, this is a problem, and this problem is called as a collision. Okay, so what is a collision? So collision is somewhere in your hash table if a condition arises where at one single index location you want to store two different values, right? So that kind of condition is called as a collision, right? So in this case, for example, if the index location is storing the number 6 and you want to store 146, so index location 6 is actually storing the number 196 and you want to store the number 146 at the same index location, but you cannot store that number because the old value will be overwritten and you are going to lose that old value, right? So this is the case where a collision occurs, right? So there are different collision resolution techniques. So you should know what is a collision, and there are different collision resolution techniques, okay? So let me just read out a formal definition of a collision. So hash functions are used to map each key to different address spaces, but practically it is not possible to create such a hash function, right? That is, it may happen that there's a hash function which is giving us a unique index locations, but if in some cases if there are more number of values which are more than the number of index locations into the array, then it is possible that there are some index location which is going to contain more number of values, right? So this is actually what I'm saying is that is kind of a pigeonhole principle. So what is a pigeonhole principle is, for example, you are having n holes like this. So this is what we are going to study in discrete mathematics, and there are a lot of applications of pigeonhole principle which is also present in the theory of computation subject. So what is a pigeonhole principle is, if you are having some holes, right? So assume that these are the n holes, okay, and you are having n plus 1 pigeons. Pigeons means the thing which flies, okay? So if you are having n plus 1 pigeons and you want to store, or these holes are going to contain some pigeons, right? Then as you can see, there are more pigeons as compared to the number of holes which are present here, okay? So assume that this is a pigeon, okay? Yeah, so this is a pigeon, and there are more number of holes, there are more number of pigeons as compared to the number of holes. Now if these pigeons wants to go inside these holes, then there must be at least one hole which will be containing more than one pigeon, okay? This is called the pigeonhole principle, right? That means if there are n plus 1 pigeons, there are n holes, then there must be one hole which will be containing more than one pigeons, so that it can accommodate all the pigeons, right? In the same way, if a table is there, a hash table is there, and assume that the hash table is having around 100 index locations. Now if you want to store, assume 123 data items or 123 keys into these 100 index locations, then there must be some holes where more than one value will be mapped, okay? And whenever there are more than one values are mapped at a particular index location, then it is going to create a condition of collision, right? So this collision is actually very dangerous because of this collision we are going to lose some data, right? And we do not want to lose any data at any condition, because data is very important, right? So we are having different collision resolution techniques. With the help of these techniques, we can actually resolve these kinds of collision, okay? So let us see some of the collision resolution techniques. So these are two different types of collision resolution technique. First is direct chaining, and second one is open addressing. Okay, and this direct chaining is also called as separate chaining. And in the open addressing techniques, we are having three different techniques. Number one is linear probing. Second one is quadratic probing. And third one is double hashing. Okay, now let us see what is direct chaining. Assume we are having this hash table, Okay, and in this hash table we want to map some values. So assume the values are 1, 4, 7, 8, 46, 148, 192, 648, 642 and so on. So assume these are the values which you want to enter into this table, and this table is containing 10 index locations. Index locations are 0, 1, 2, 3, 4, 5, 6, 7, 8 and 9, right? So the first number is 1. So if we do 1, let me just save some spaces here. So if we do 1 mod 10, because the size of the table is 10, then we are going to get the index location 1. Therefore at the index location 1 we are going to store this 1. Okay, the next number is 4. So if we do 4 mod 10, then we are going to get the number 4. Therefore at the index location 4 we are going to store this 4. The next number is 7. So if we do 7 mod 10, then we are going to get 7, and then we are going to store 7 at this index location, right? So remember, this is a hash function, right? So where hash function is key mod n, right? So the next number is 46. So if we do 46 mod 10, then we are going to get the index location 6, and we are going to store 6 here. Okay, and then we are having 48. So if we do 48 mod 10, then we are going to get 8. So we are going to store 8 at this position, right? So this 48 at this position. The next number is 192. So if we do 192 mod 10, then we are going to get 2. Therefore 192 will be stored at this index location. Now if we do 648 mod 10, then in that case we are going to get 8. So but if you see at the index location 8, there is only one data which is present, which is 48. So what we are going to do in direct chaining is we are going to create chains in this hash table, and this chains will be of chains of linked list. Okay, so that means we are going to create a node like this, and in that node we are going to store this number, which is 648. Correct? So the next number is 642. So if you do 642 mod 10, then we are going to get the number which is 2. Therefore we have to store 642 at this location, but there's only already 192 which is present at this location. Therefore we are going to store 648 like this by creating a node here. Okay, so anytime whenever there's a condition encounters where there's a collision in this direct chaining technique, so what we are going to do is we are going to create long chains. We are going to just create new nodes, and we are going to add chains of the data here. Okay, this is 642. Okay, so we are going to add chains in the data, right? So this is called as a separate chaining technique. So next technique is open addressing. So let us see what is an open addressing. Now in the case of open addressing, there is a first technique which is called as linear probing. Okay, so in the case of linear probing, whenever there is a collision occurs, then we are going to calculate a rehash function. Okay, and what will be this rehash function? So this will be let me just explain you with the example here. For example, this is your hash table, and it is containing some data, and there are 10 index locations here, right? So this is 0, 1, 2, 3, 4, 5, 6, 7, 8, and this is 9. So these are the 10 index locations, and the numbers which you want to store into this hash table are 192, 92 maybe, 146, then 646, 646, and then assume 91, then 93, 97, and so on. Okay, so the first number is 192. So if we do 192 mod 10, then we are going to get the value 2. Therefore this 192 will be stored at the location 2. Okay, the next number is also 92. So if we do 92 mod 10, then we are going to get the number 2. But in that index location 2, as you can see, there's one data which is already present, and the data is 192. But we want to store this 2. then what is the position, or where should I store to? Because it is important for us that we should store this number, right? So in that case, what we are going to do is we are going to find a rehash key. There is some other location where this data should be inserted. Okay. So generally what we do is, if for the first time we are applying this hash function, then in that case we just do key plus I mod n, right? So key plus I mod n is our hash function in case of linear probing, and this I is some integer value. So here it starts from 0, 1, 2, 3, 4, 5 and so on. So when the value of I is 0, in that case we are going to do 92 mod 10. So but in the play position where we are having 92 mod 10, that's we have got the position which is 2. When that position there is only one other data is present, therefore we are going to increase the value of I. So next time we are going to calculate 93, or you can say just simply 92 plus 1 mod n. So we are going to get the location which is 93 mod n. So the location is 3. So in that case, the index location 3, this 92 will be stored. Okay, as you can see, whenever I am going to get a collision, I am just going to increase the value of I. That's it, right? And this value which I am increasing is by 1 only, that is 0, 1, 2, 3, 4, 5, 6 and so on, right? So the next number is 146. So if we do 146 mod 10, then we are going to get the value 6. So this 146 will be stored at the location 6, right? The next number is 646. So if we do 646 mod 10, then we are going to get the value 6. That means this 646 should be stored at the location 6. But as you can see in the location 6, we are already having some data, and the data is 146. So we cannot store this data. So what we are going to do now is we are going to calculate the next location. So how will you calculate the next location? By using this hash function. That is, you are going to increase the value of I. So the next time this will be as 646 plus 1 mod n. So which is going to give us the location which is 7. Therefore this 646 will be stored at the location 7, right? Now the next value is 91. Okay, so if we do 91 mod 10, then we are going to get the value 1. Therefore this 91 will be stored at the index location 1. There's no problem in that case. Why? Because the index location 1 is already empty, right? Now if you want to store 93, then you do 93 mod 10, then you are going to get the location 3. But if you see, the location 3 is already filled. In that location I have stored 92, right? Therefore what I am going to do is I am going to calculate the next value. So in the next value I am going to increase the value of I. So it will be 93 plus 1 mod 10. So that number will be 94 mod 10. So which is going to give us the location which is 4. Therefore this 93 number will be stored at the index location 4. Right? Now next is 97. So if we do 97 mod 10, then we are going to get the index location 7. Therefore, but in the index location 7, there is only some other data which is present, right? Therefore, we can just increase the value of I. So it will become 98 mod 10, which is going to give us the index location 8. Therefore, 97 will be stored at the index location 8, right? So this is called as a linear probing. Okay, and the value by which we are increasing this I every time whenever we are getting this collision, that this value is called as a step size. Okay, but there is one problem with this linear probing, and the problem is called as clustering. So what is this clustering? Okay, assume that you are having a hash table, right, and you are having some data. So assume the data is 7, 77, 177, 187 and so on. Okay, and you can see whenever I am going to try to hash these values into the hash table, right, and maybe the size of the hash table is 100 or 1000 or so on, then in that case you can see there's some portion of the hash table which is filled in a dense way. So when I'm saying filled in a dense way, that means all these locations are containing some data. So this location, this location, this location are containing some data, but all the other locations in the table is actually empty, right? That means some portion of the table is actually clustered, right? This, all the data is dense in that case, right? In that portion, and rest of the table is already empty, right? So this kind of problem is called as the clustering, right? So this is a primary clustering. So there are different kinds of clustering which we categorize. One is primary clustering, second is secondary clustering, right? So here this condition is primary clustering, right? So when we encountered the primary clustering, so we thought that maybe by increasing the step size, I can reduce this primary clustering. Okay. Now, how will you reduce the primary clustering? By increasing the step size, right? So maybe assume that the value of the step size is 2, right? That means whenever I encounter a collision, that at some point of time, I'm going to jump by 2 steps. So let me just take that example. Let me show you what is happening in that case. Okay. So assume you are having this table, and this table is having 10 index locations. 0, 1, 2, 3, 4, 5, 6, 7, 8 and 9. Okay. And the values which you want to map in this table are 196, 46, 186, 786, 136, 142, 146 and maybe 138. Okay. Now let us try to map this table, right? And here the step size will be even numbers. Okay. So if the hash function which we'll be using is key plus I mod n, right? And the value of I can be 0, can be 2, can be 4, can be 6 and so on. That means the step size is actually 2. Right. So if we get the first number, it is 196 mod 10, then we are going to get the location which is 6. Therefore, we are going to store this 196 at that location. Okay. Now the second value is 46. So if we do 46 mod 10, in that case, we are going to get the value 6. So, but in the index location 6, there's only one value which is present. Therefore, we have to increase the step size now. So what we are going to do is 46 plus 2 mod n. So when we did 46 plus 2 mod n, then we are going to get the location 8. Therefore, we are going to store 46 at that location 8. Right. Now the next data is 186. So if we do 186 mod 10, then we are going to get the location 6. But there's only one data which is all present in the location 6. Then we have to do 186 plus 2 mod 10. Then we are going to get the location which is 8, but there's already one data which is present at the location 8. So we have to do 186 plus 4 mod 10. In that case, we are going to get 190 mod 10, which is 0. So we are going to store 190 at this 186 at this location, right? Now the next data is 786. So 786 mod 10. Then we are going to do we are going to get the location 6, which is already filled. So we are going to find 786 plus 2 mod 10. Then we are going to get the location which is already filled. Then again we are going to do 786 plus 4 mod 10. Then again we are going to get the location which is already filled, right? So then we are going to do 786. Let me just use this space. Then we are going to do 76 plus 6 mod 10. Then I'm going to get the location 2. Therefore, this 786 will be put at this location 2. Okay. Right. Now we are getting the value which is 136. So if I do 136 mod 10, then again I'm going to get this value location 6. Then I'm adding 2 to it, then it will be location 8. Then I'm adding 2 to it, then it will be location 0. Then I'm adding 2 to it, then it will be location 2. Then again I'm going to add 2, then it is going to give us the location 4. Therefore 136 will be stored at this location 4, right? Now the next data is 2. But if you get the data 2, this 42, then you are going to get 42 mod 10, which is going to give us the location 2, but 2 is already filled. So we have to increase the step size. Then we are going to get 42 plus 2 mod 10. Then we are going to get the location which is 4, but the location 4 is already filled. And again we are going to increase the step size. So we are going to do 142 plus 4 mod 10. So we are going to get the location 6, which is already filled. Again we are going to do this 42 plus 6 mod 10. Then we are going to get the location 8, which is already filled. So again we are going to do this 42 plus 8 mod 10, then we are going to get the location 0, which is already filled. So we are going to do 42 plus 10 mod 10. So we are going to get the location 2, which is already filled. Then 142 plus 12 mod 10. Then again we are going to get the location which is already filled, and so on. So that means even if your array is containing some free spaces, here the free spaces are at the index location 1, 3, 5, 7 and 9, and still you cannot store the data. Why? Because your step size is actually giving us the location which are already filled, right? It is just keeping us in an infinite loop, and it is saying that array is already filled because I cannot find any location where I can add this data, right? So in this case, as you can see, the step size is very important thing. So if you choose the wrong step size, then you are going to get this kind of condition where you are just going to fill all the even locations, but all the odd locations are already empty, and we cannot add the new data into the odd locations because our hash function is not giving us the odd locations, right? So that is why the step size is very important. So the question is, what should be the appropriate step size where we can map all these locations uniquely, okay, or effectively, and we can remove this primary clustering and we can remove the secondary clustering, right? So this condition is called as the secondary clustering, that here in this case I have filled all the even locations and I cannot put any other data. So this is a secondary clustering. So the first was primary clustering, where all the data was actually densed or condensed at one single position, around one single location, okay? So the question is, what should the step size so that I can remove this kind of issue, okay? So as you can see, it turns out that you can say that if you are having key plus I mod n as the hash function, and if you take I and n, if they are co-prime, now if these two numbers are co-prime, then the step size is actually going to map all the index locations uniquely, right? For example, if you take the value of I is 3 and 10 and 3 are actually co-prime, so when they are co-prime, then you try to execute this into this complete array, into this hash function, try to execute this, make the value of I as 0, 3, 6, 9, 12 and so on, then you'll see that it is going to map all the locations in the unique index locations evenly, right? So this was the first method in open addressing, which is linear probing, okay? Now let us see the second method, which is quadratic probing. So it is quadratic probing. So in the case of quadratic probing, we just changed the hash function, okay? So here, whenever we are going to get the collision, in that case, we are going to say that if there's a collision, then the rehash of the key is going to be n plus k square modulus table size, okay? So this k can vary from 0, 1, 2, 3 and so on, right? For example, if you are having the following data, the data is 31, 19, 2, 13, 25, 24, 21 and 9, right? Now if we are having these following values and the size of the hash table is actually 10, or maybe let's change the size of the table, make it 11, okay? So we are having this table with 11 index locations. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So in this case, the first number is 31. So we are going to do 31 mod 11. Therefore, we are going to get the location 9. So we are going to store 31 at the location 9. Then the second number is 19. So 19 mod 11 is going to give us a number which is 8. So 19 will be stored at the location 8. The next number is 2. So 2 mod 11 is going to give us the number 2. Therefore 2 will be stored in the index location. 11 will be, this 2 will be stored in index location 2. right? So next value is 13. Then we do 13 mod 11. In that case we are going to get the location 2, but as you can see in the index location 2 there's already one value which is 2, so we haven't stored this value. So what we are going to do is we are going to increase the value of k. So it will be next time n plus 1 square. This n is actually the key, so you can say key plus 1 square modulus table size, and this table size, then actually I changed the terminologies. Okay, so you can say this key plus 1 square mod 11. So here this will be 13 plus 1 mod 11, which is going to give us the location 4. So, or you can say it is going to give us the location 3, because 14 mod 11 is actually 3. So we are going to store 13 at the index location 3, right? So if we say the next number is 25, if we do 25 mod 11, then we are going to get the index location 3, but at the index location 3 13 is already there, so we are going to increase the value of k. So it will be 25 plus 1 square mod 11, which is going to give us the index location as 4. So this 25 will be stored in the index location 4. The next value is actually 24. So we do 24 mod 11, then we are going to get the index location 3. At the 3 there is only some data, then we are going to increment the value of I. So it will be 24 plus 1 square mod 11. Then again we are going to get the index location 4, which is already filled. Then again we are going to do 24 plus 2 square mod 11, which is going to give us the index location which is 20. This is 28. 28 mod 11, and 28 mod 11 is going to give us the index location which is 6. So we are going to store this number 24 and the index location 6 and so on. Okay, so you can follow this technique in case of quadratic probing. So whenever I am saying this linear probing, quadratic probing and double hashing, all these different functions are having different hash values. Okay, or you can say so all these different tables are having different hash functions. Okay, now let us see double hashing.